Всем добрый день.
Доброе утро.
Ну ладно, уж утро-то честное. Квиз начнется через минуту. Начинаем. Осталась минута. Сдаем. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ответы больше не принимаются. Давайте пройдем по правильным ответам. Окей. Advantage of Gini impurity is there is no logarithm to calculate, so it's just faster. No, we do not need to scale features because we just use thresholds. What is the difference between oblivious decision trees and regular decision trees? Is that in oblivion decision trees, one level is one feature. So the same feature on one level. Name at least 3 methods of regularization. Well, the obvious ones are minimum error and cost complexity and max depth, for example. There are others, such as limiting the number of data points in leaves or in nodes or something else. We actually go through regularization a little bit more today. Any questions?
Все понятно.
Good. Okay, let me turn on the camera. Yes, please turn your cameras on as well. Thank you very much. Thank you. Okay. Just a second. I'll sort out Zoom stuff. Okay. There it is. Okay, here's the chat. Here's participants. And okay, here's the sure. Okay. So today we're going to talk about ensemble methods, and mainly we are going to be focused on ensembling trees, of course, because like state of the art currently in machine learning and classical machine learning, working with table data is decision trees. So what do I mean when I say ensemble? I mean, we combine several methods together, several classifiers or several regressors. And the easiest way to do that will be through voting, right? So here, for example, I have 3 classifiers. I have a decision tree with depth of 4. I have k nearest neighbors with k equals 7, and I have a kernel SVM with a polynomial kernel. So you see there are sort of advantages and disadvantages to every method, and the logical thing to do would be to combine them together. All right, so we can have insight from one, can have insight from the other, and we can even gain stability and resistance to overfitting if we combine them. So here is a combination, for example, right? So we have 3 decision here, tree decision here, but somewhere in between there are like KNN or SVM decisions, which are not straight, right? Now, there are two types of voting. You can have hard voting and soft voting. Hard voting is we just count the number of positive numbers, right? So we say, okay, for example, for this point, there's one vote red, one vote green, and another one vote green, right? So you can say, okay, this point is green. Now, what we can do instead is do a soft voting. A soft voting, that's something that looks at the how algorithm is sure or not sure in its decision. So for example, let's say we have a plus class and a minus class, and we have one, two, three algorithms. And this one says, okay, this is a positive class, but the probability of that is, well, let's say 5149. And this is the same thing, right? And this says, okay, I am really sure it's class minus, right? Now, what will happen if we do a hard voting, then this will have 2 votes and this will have 1 vote, right? Because there are 2 classifiers, say this is positive class. Now, a soft voting can take an account probability. So for example, the easiest way to do is just to sum it up, to sum up probabilities. So this will sum up to 1, 2, right? And this will sum up to 198. So in here we can see this is a higher chance actually of being minus, because these two are not actually sure. So they have to make a decision, but they're not actually sure in this decision, right? Another way would be to multiply those probabilities, because those are probabilities, right? So we can multiply them, or sum up logarithms, because we don't actually like to multiply small numbers many times, but maybe if there are many classifiers, we would prefer to first take a logarithm and then sum it up. Again, when we talk about ensembles, we mostly talk about random forests, which are ensembles of different trees. However, if you take a data set, a training data set, and you apply some tree building algorithm to it, many times you will always get the same tree, correct? Because we always find the best feature and the best threshold according to our information gain, and end up with the same tree every time. So how do we change? How do we come up with the ensemble of trees, right? To random forests. Well, we need to randomize something. What do we randomize? We randomize data. So there are 4 ways to do that. One is just take a subsample of data, right? Let's take a half of data, a random half of data, and build a tree on that. So we build several trees, and every time we take a random subsample of data, then we will have different decision trees, right? Because we take random subsample, we take different decision trees, and those different decision trees will give us sometimes different decisions, but we can add it up by hard voting or soft voting. Doesn't matter, right? Because there is a threshold again. So here, for example, probability of both classes is 0.5 and 0.5, right? So we still have those probabilities. So we can apply soft voting. Now, another thing is having a sample of features, right? A very, very good way to randomize the trees is to just give a tree access to just a subsample of features, right? So you cannot use, they cannot find the same feature and the same threshold then, right? Now, combining those will give us random patches. So we can sample from both features and examples. Why is it called random patches? Well, you can sort of see if you take random features and then random sample. So you sort of take the random patch, right, from your data. So this is why they're called random patches. And the last, but actually most commonly used one is bagging or bootstrap aggregating. And the idea is quite simple. Let's get the same size data set, from our data set. So let's say we have n points. We need a data set, not a sample, but we want a data set that also has n points. But how we do that is we put those in the bag, and we will take, okay, I'll try to draw a hand. We'll take a point from the data set and we'll put down it in the list, right? So it's okay. I put point in the back, take the point, look at it. Okay, the first point is this. And then I put the point back. So and then I take another one. So there can be repeats, right? So there are random points from our data set, and that can be repeated, and some can be repeated, but some can be excluded from this list, right? So we have the same size, but some are repeated. Another way to think about it, and actually in many ways correct, because we're going to use it a lot in the next one. So let's say we have our initial data set with n points, and instead of having weights 1, right? So when we build our algorithm, every point weighs 1, but we already saw last lecture with fuzzy decision trees, right? So if we change the weights, the algorithms still work, right? All our algorithms still work if we change the weights. So instead we can say, okay, some we exclude, right? So say, okay, some are 0, we don't need them, but some have weights 2 or even 3, right? So instead of having a new data set and sampling from it, we can just take and assign random numbers according to some distribution. And Poisson distribution is most commonly used to try to imitate this bagging process. Now, I mean, you can even go to of course, not an integer number, right, but a float number. So a fraction, you can say, okay, this is 3.7, or this is 0.5. It doesn't matter. You reweight your points, the algorithm still works, but you get a random tree. Now, bagging, even though I used an analogy with taking a bag and taking out points, actually bagging is an abbreviation from bootstrap aggregating. And bootstrap is a statistical method that does just that. If you have a sample and you want to evaluate some characteristic, what you can do is resample that sample, right? You can assign weights, calculate the characteristic, do it again and again and again, and then average that characteristic. So you sort of create more samples from the sample you have. Why is it called bootstrap? So aggregating, quite easy, right? So you aggregate your data, right? Why is it called bootstrap? And anyone knows what a bootstrap is? Any ideas? Okay, a bootstrap is actually a common household thing, and you can see on your shoes, on your boots, right? So if you have a bootstrap is a small loop that helps you put on a shoe, mostly like a sneakers or something, right? I have one, but I'm not gonna go there. Now, why is it called bootstrapping then? Well, statisticians actually so a bootstrapping is actually an evolution of a method called jackknifing. So a jackknife is just a simple knife that is always useful, and sort of was again a method that is always useful. But a bootstrapping has a more sophisticated story. So you probably know a tale of Baron Munchausen or Münchhausen in German or Russian, but in English it's Munchausen. And the story where he got stuck in some tar with his horse, and he pulled himself up by his hair, right? Well, in some translations, he does it by his bootstraps. So instead of pulling out by his hair, he pulls himself up by his bootstraps. And there is actually an English phrase, pull yourself up by your bootstraps, means to have something from nothing, right? To have some, just by sheer force of will, pull yourself out from the situation. And here we have sort of the same thing, right? We don't have that additional data. To create additional data from initial data. Now, random forests are random. So we randomize the data to create trees. Then the final result could be determined by the hardest of voting. There is another way. If you have a very, very small data and it doesn't actually make sense to build a tree because every tree will be overfitted to a particular sample, you can use extremely randomized tree. What are extremely randomized tree is not only do you use a subsample of data, but you also use a random tree algorithm. So you just create random trees. Well, they still will classify somehow the points, but by building a forest of those trees, you can actually have a classifier that works sometimes. It's extremely random trees. Now, even though we have random, we build a forest, every tree is independent from others, right? So to build a tree, we can say, okay, this tree, we only have data sets, so we can get the data set to a training algorithm, and we can even parallelize all those trees, right? Send this data or just a table of weights actually to that node, build a tree, build a tree, build a tree, and then take it back. Now, we can go about it in a different way, right? So let's build one tree, see how it classifies the points, and maybe we can actually reweight the points in a specific way, not doing it at random, but invent a way to reweight those points so that another tree can learn from the first tree and say, okay, that tree got something right, I'm going to get everything else right. So instead of having a random building, we can have boosting. A boosting is addition, right? So you boost your previous decision by the next tree. And the first algorithm we're going to go through is adaptive boosting. So, or ADA boost. So adaptive boosting, again, starts with weights. Like it's an algorithm of reweighting points, basically. You still build the trees sort of the same way, but just build small trees. So you have a weight distribution for your data set. So you have for point I on step 1, right? So D1I is the weight of that point, and they're all equal. So if you have n points, every weight is 1 over n, right? So 1 over n for every point in your data set. Now, we train a weak hypothesis, and weak 3 hypotheses are called stumps. Well, actually, stump is a very specific thing, right? A stump is a tree with the depth of 1. So this is a stump. Right? We just divide one time. And a stump, if you don't know what a stump is, in Russian it's pень, right? So it's a very, very small tree. So you build a weak hypothesis HT by either using weighted impurity or weighted sampling. Well, it doesn't matter actually. So you either sample with those weights, or you just use weighted impurity. So it's the same thing, right? So you just use the same points, but only use with the weight. And now the thing is, you need to find the minimum error. So you find the best threshold and the best feature, sort of the same way, and you minimize the error. Right? So the error is still 1 if we guessed it right, and 1 if we guessed it wrong, and 0 if we guessed it right. Right? So it's still a binary classification error, 1s and 0s. But it's weighted. right? So if before that we calculated, so before that the error was the sum of errors divided by n, right? So this is what error. Now we have it weighted. But on the first step, it's still the same, right? Because this is 1 over n. So first step, the same. We just do a one step of tree algorithm. Just do a stump, right? And this thing will need in the future, we need a weight of hypothesis. And the weight of our hypothesis is with that formula. And well, let's draw it so we can see how it looks. So this is error, total error from 0 to 1, right? So 1 is the maximum. If all ones, then it's 1. And this function looks like this. So it goes to infinity when this approaches 0, and it goes to minus infinity when this approaches 1. Now, well, we don't actually use, negative points from it. Why? It's the same thing as having a area under the ROC curve lower than 0.5, right? If we did something where the error is actually more than 0.5, right? We just reverse our decisions and it will be lower than 0.5, right? We just sort of mixed up the classes. So the only outcomes are positive here. So the weight, we only look at the weight in this area. And the lower the error, the higher the weight. Now, what is the main step? So this is just a classification, small tree, the weight. The main step is we then reweight the points. And how should we do it? Well, let's think about it. So the next error, right, will be still calculated by that point. So let's say the point is classified correctly. Should the weight of that point on the next step be higher or lower? What do you think? Any ideas?
Первое дерево научилось определять на каких-то точках, то логичнее другие на других точках определять.
And that means?
Значит, должно уменьшиться.
Yes. So this should get lower. And if it's not correct, all right, so the weight should get higher. How higher or how lower? Well, a simple algorithm. So we take the current weight and we multiply by the exponent to the power of alpha t, right? Where alpha is the weight of our hypothesis. So this alpha goes from 0 to infinity. So this goes from 1, right, to infinity as well. So this is always positive. Not only positive, but it's higher than 1, right? So when we multiply, if the point is incorrectly classified, every weight will be increased, right? Because this is 1 or more. And for correctly classified points, we multiply it by exponent in the power of minus alpha. So we decrease those weights. And then, of course, we need to normalize it. So the sum is still 1, right? So we need the sum to be 1. So it's divided by the sum of weights. And we do it, well, until convergence, basically, until there is no more. So until we reweight in another way and we cannot find a good classifier, or the weight becomes so small because it's in something near 0.5 always. After that, we have a forest, right? So we have many stumps, and each one produces a decision. and each one has weight. And we can, after that, do a hard voting or a soft voting, right? So if we do a hard voting, every vote counts with coefficient alpha. But if we do a soft voting, we calculate the probability, right? And then we apply alpha. Yes, alpha is from here. And yes, this is the same alpha. Okay, so this is an AWS token. It's good to see it in an example. So here we have two features. We build stumps. A stump is just a division by one of the other feature, right? And at first, so we have orange triangles and blue circles. And at first, their weights are the same, and the size of the weight would be the size of the point. I have a question from chat, and let's go through that example. And maybe the example will make it clearer. And then if not, you can ask it again. So if all the weights are the same, then algorithm finds the best threshold, so a best stump by feature 2, and it divides it like this, right? So now let's say, okay, these are classified correctly, these are classified correctly, and these are classified incorrectly. So the weight will lower for those, and will go up for those. So these are bigger now, and these are smaller. Now, after that, we see that the weight and the error, the influence of on those points on the error is lower, right? And if we take the weighted error, then the lower error if we divide it like this, right? So now these are correct, but these are wrong, right? So these should go down, these should go down, and these should go up, right? So now we say, okay, but they go down not from the initial, right? So they do not go down from this, but they do go down from this. So in actuality, this weight is bigger than the initial weight because we first went up by a lot and then down not that much. So now the best classifier is this one, right? So we actually do need to classify all the blue points correctly, and the orange ones have low weight. After that, so we have 3 classifiers, 3 stumps. We do a hard voting, right? So let's say, so here and here. So let me draw everything. So these are our 3 classifiers. So let's say blue to orange, right? So this is 3 to 0, right? So 3 vote for blue and none votes orange, right? This is 2 to 1. This is 2 to 1, right? This is 1 to 2. This is 0 to 3, and this is 1 to 2, right? So you see, by just reweighting the points, having different classifiers, we end up with, well, in this case, a perfect classifier. Is it clearer now, Yuli? Good. Any other questions for adaptive boosting algorithm? Okay. Now, we still end up with a voting scheme, right? So even though we add our decision up, sort of, every tree still tries to take in all points, even though reweighted, and classify them all. Now, so this is adaptive boosting. Another way is gradient boosting. And gradient boosting, we'll first go through a simple way of explaining what a gradient boosting is. and then we'll go through the math, and you will all probably die. But those who will not die will know about gradient boosting, which is a very, very cool algorithm of building trees, and it works best. Okay. Now, simple way. A simple way is to say, let's build a hypothesis that is the sum of hypotheses, right? And we'll first look at gradient boosting for regression, because it's easier for that example, right? So let's just forget that we have a classification problem. Let's say, okay, well, let's build a tree for regression, because we have adaptive boosting for classification, and it's hard to do regression there. Possible, but hard. But with gradient boosting, it's easy to imagine regression, because we add up the weights, and that they will add up to some number, right? And that number will be the answer for regression. So let's say we need a final hypothesis that will be just the sum of small hypotheses, right? And if we build it sequentially, that means, so if a ht plus 1 is ht plus small ht plus 1, right? So we build one, so this is what they actually built, a weak hypothesis. Then we want this sum to approximate some label, to approximate the correct outcome. Then this means, logically, that we want this small hypothesis to approximate the difference between the label and the current big hypothesis, correct? And this one is called a pseudo-residual. And it's called a pseudo-residual because the name residual is sort of taken by linear regression algorithm. So this is what they call it in trees. Now, well, it's easy, right? So you just build a tree, you limit its depth, but it's not stumps. In gradient boosting, we limit by something like 5 or 7, the depth of 5 or 7. So it's still small, but not a stump. So you build a tree with the same algorithm, although you approximate a residual now. And then you add up your trees with their values. Let's go through an example. I think it's easy. So let's say we have a function, right? This function, green, and we'll try to predict. We only have one feature, x, and we try to predict y. So we build a tree, and in this case, the depth is 2, right? So just 4 leaves. So the first tree is this one. So we first divide like this, then divide like this, divide like this. All right, so this is the tree, sort of looks like. It's a symbolic representation. So, right, so how we divide by one feature. Then we subtract, right? So we need to subtract from our data point the value of the tree, right? So we subtract from this point, we subtract the value of the tree, and this point will just goes to 0, right? Because it is right on the leaf, right? Same for this point, for example, right? This point goes to 0 as well. But the rest, there are still some residual or pseudo-residual left, right? So this value. Okay, so let's build a tree that fits that pseudo-residual. Well, it's something like this, right? So we divide it here, then here, and here, and we subtract again, right? So now we only have those residuals, and the residuals are getting smaller, which is good. Now we build a tree, and you see, like here, the residuals are very small. So now if we go and add it up, so we sum it up. So we have this one, then if we added this one up, it's something like this, right? This is this one. And if we add this one up, it's something like this. So the final tree fits the data better. Is this explanation clear for the gradient boosting algorithm? Yes, good. The last thing is, so we fit to pseudo residual, but in practice, we do not add it with just a coefficient of 1. We add a learning rate. Why? Well, it just works better. That's like a conceptually easy answer. There's another reason, right? So let's say we have sort of our goal, right? So let's say this is a correct decision, but when we look at the residuals, we sort of change the data set again, right? So this is where we go if we look at residuals. So if our starting point is this and we try to add up trees, so let's say we look at this point, right? And we go here. Now we'll look at this point, then we'll go here. Now we go to this point. So this is what will happen if we just add 1 every time, right? Now, let's say we have a coefficient, which is lower than 1, right? So let's say we want to go here first. So we not go there straight away. We just move here. All right, then we go here. We only go here. And we want to go here. So by doing it in small iteration, we sort of move in the correct way, right? And then we can even go back at some point. We'll still be somewhere around here from now on. Go slower, slower, slower. And we end up in the correct way. This is sort of, if you remember the argument about average hypothesis. The average hypothesis is very close. And we try to average them by going not to them, but, you know, lowering the speed. Now, good news. There are many gradient boosting algorithms, 3 main libraries. The first one was XGBoost, or extreme gradient boosting, which is independent. Then there was a light GBM from Microsoft and a CatBoost from Yandex. And the best one currently is CatBoost. So this is the one mostly used by researchers and practitioners. It's very good, it works fast, and it's always updated because this is one of the pride possessions in the Yandex open library. Okay, now let's get to the math. Oh, this one is simple, right? Sort of the same. HT, sure. Now, what do we want to minimize? We want to minimize some error of this final hypothesis and why. And let's right away add regularization, right? So the regularization, hopefully some additive function that regularization for the whole tree is a sum of regularizations for trees. We can do it easily, and you'll see that it will hold up. Okay, now this and the regression case was just the difference, right? So we want to minimize the difference. Well, actually, we mostly wanted to minimize the square. All right, so this was just the sum divided by n points, right? So this is what we wanted to minimize when we did regression, and we did it by just approximating average and so on. Now, this does not have to be a regression loss anymore. This can be a classification. How would we do that? Well, L in that case can be a, let's say we want to do a classification. So this H is still a number. It's still the sum of weights in the leaves, right? And this h is a number that is written in 3t for point x, right? So ht of x is a number that's written in the leaf. And big H is just the sum of those numbers. But if you have a number, how do we do a classification, right? So, and how do we say we want to minimize that loss? Well, we can go, if we do a binary classification, for example, then we do a negative log likelihood, right? So we get log, and the likelihood would be the probability. How do we go through probability? We go through sigmoid of that H and multiplied by the class, where a class is +1 or -1. Right? And we still can add it up, right? Because if we add up negative log likelihood, we calculate the full negative log likelihood, correct? So this L now becomes this one. And you can add it up. Now, this is a very important point to understand, that this L function is no longer a regression function. It can be anything. And what is more, it includes the transition from a number to classification in that L function, right? So H is still just a straight up number. It's a number. So if we have a tree, it's a number that is written in the leaf, right? There's some W. We'll use W's. Why not? But then we can go from this H to a classification, and then we can calculate. So if it's positive, then it's a probability of positive class. If it's negative, then it's minus the probability of negative. So it's, you remember from the logistic regression, you should remember, right? So we embed in this L function, we embed both the classification, right, part. So sigmoid from that H is the classification, and the loss function for classification, because H is still a number. And this is very, because some people get confused, right? Some say that this is already an output, right, of, let's say, the weight of X, but it's not. Then the math will not work because you cannot add it up, right? So you still need to add up numbers, then take stuff like that. So H is still a number. Okay, next. Well, again, nothing fancy. Let's separate the last hypothesis that we're actually working on, right? So let's say that this is already built and we are currently on the step T. So we need to build this one, right? And this regularization, again, is already done. So we only need to build this one. So we need to find this one and find this one. Okay? Now, we can still do it, right? Because H is just a sum, big H is sum of small h's, right? So here is just number that we add up, right? Math still works, thankfully. So this is just two numbers that we add up, we can separate them, no problem. Still works. Now, so if we want to minimize this loss or error, in this case, it can be a loss, doesn't matter. Then using a, let's go, using a Taylor approximation, we can say, okay, if we want to, so this is some number, right? This is some number, and we have a function that depends on this sum, and it doesn't actually depend on this, so it doesn't matter. So we can approximate this by saying, okay, we can approximate it by the value in the point, this one, ht minus 1, plus the first derivative of that function in the point ht minus 1 times ht plus 1 over 2 or 0.5 times second derivative in that point times ht squared plus something else after that, but it's getting lower and lower. And sometimes there is even nothing there, right? So you can go, if the third derivative is 0, then you just end up with 0. Plus, we add up the regularization for the last one, but this is a constant, right? So this is some constant function. We don't need to optimize it. So we want to optimize this. And this is also, in our view, a constant function, right? Because we already built it, we cannot change it, right? So we just can, okay, this is something that we cannot change. Then this, because this is a sum, that means we only need to minimize this plus this, right? So only minimize this plus this one. Is it clear so far? There's a question about 0, 1 in the chat. Was it about the when we talked about binary classification, right? The cell function?
Да, вы там, когда писали функцию потерь, там,
Yeah.
там разве не 0,1 должно быть под логарифмом у y?
No. Why?
Ну, соответственно, логарифм получается. Ну, логарифм.
Yeah, because it's sigmoid of YH. Yes. Then it's correct. Yes. Sorry about that. Yes. So, this is, of course, +1 or -1 because it changes the sigmoid, right? So this is negative, this is positive. So, yeah. It's sigmoid of YH, of course. Thank you for that question. Okay. Is this clear? Well, and for example, for mean square error, right, we want to minimize this. Right, because we calculate the first derivative of square is just this, and the second derivative is just 1, or well, I mean 2, right? So the first derivative is 2. Okay, so that's the first derivative of the square would be 2 of this, right? If this is the point where we calculate the derivative. And the second derivative is just 2, but it's 1/2, so it's multiplied by 1/2, and this is 0. So no, 0, 1. So for mean square error, this is the function. Right? Okay. Is anything like confusing like so far? Like this is a not very complicated math, especially for you, right? You had a good math background, right? Before you came to me. So, but still can be confusing. Is everything clear? Because it's gonna be more crazy after that. Yeah. Okay. So let's talk about regularization. So we want to regularize something additive. And well, let's just do it like that. So for XGBoost, like there are different ways to regularize, but XGBoost, which was the first one, regularizes with the number of leaves and the sum of squares of weights in those leaves, right? So this is just a number of leaves, and we calculate for that number, right, the weights squared. And this is additive. It's easy to see that this is additive, right? So a sigma of all trees, the leaves are just added up, right? And the squares, again, are just added up. So you have many small trees. For final functions, just the sum of those functions. So this formula works for us, right? So we can say that this works because you see what the regularization function is. Okay. Now, let's rewrite some equations. So let's introduce a function q of x, which is the number of leaves. So in this particular case is j. It's the number of leaf that x belongs to, right? So h of x would just be the number that stands in the leaf q of x, right? Just number, right? So, okay. So this is how we rewrite. So this, we just change this for this and this for this squared. And then we can use, well, you see where I'm going, right? So here we calculate from 1 to n, but let's now switch from calculating over leaves. Let's group all the points by leaves, right? So we will sum it up. So we'll change the sum from 1 to m here, right? This is just the weight for all x's that belong to the leaf j, right? So we just grouped by those leaves, right? And we can put that weight squared, because this is a weight squared and this is the weight squared. So we can say, okay, this is the sum of v, which is the second derivative from the last slide, plus lambda, which is here. Right, so we just grouped it, and there's just gamma left. Is it gamma? Sure. Okay. Is this still clear? This every step is quite simple. Yes. Okay. Now let's rename those grouped variables by big U and big V, right? Or a capital U and capital V. So uj is just a sum of weights for points in the leaf j, right? And vj is this, not the weights, but the first derivatives, right? And v is the sum of second derivatives. So some value, so some first derivative, some of second derivatives. Okay, so this becomes then this. Now, let's solve it. So we need to find the minimum of that error or loss function. So let's first find the minimum W. So let's say we have V's and U's. What does it mean? Let's say we have some tree built, right? Because U's and V's depend on thresholds, right? On rules. So how do we separate? So we separate by some threshold, right? And we end up with the separation. So if we have the separation, so if U's and V's are defined, then we can find the optimum W. So we can calculate from that error, because we want to minimize it. We can calculate the best W to put in those leaves. How do we do that? Well, just by solving, right, the derivative. So we say, okay, the minimum of the square, find the first derivative, it should be equal to 0, solve that equation. Then this is just, so if we find the derivative, so this will go here, and this will, right? And this should be equal to 0, right? And this will disappear, correct? This is the derivative. So then W is just U minus U divided by Vj plus lambda, correct? So this is the optimum weight. So if we have a separation, if we have all the thresholds defined and the tree built, then we can find the optimum. So we know what would be the optimal weight for any given separation, any given collection of thresholds. But since we know now the optimum weight, we can put it back here, right? And we calculate the optimum. Right? So this is squared, right? But it's still easy. This is squared, right? So this will cancel. So we'll end up with squared over V alpha. And this, if we put here, then this is just squared, right? So they're the same. So we end up with this, which is the optimum loss. What do we do now? Well, now we launch a tree algorithm because this is sort of our impurity. And we can calculate the information gain, right? So we can build a tree, find the best tree, because now we have a measure, because this only depends on thresholds, right? So for every threshold, we can actually calculate the information gain, right? So the gain for any threshold, if we have a right and left separation, is this, right? So for every point, we only need to calculate for every point the u's and the v's, right? Because u and v's are predefined for a point. And once we've written, so for every point, we've written the first derivative and the second derivative of the loss function that was on the previous step. We can now, using those u's and v's, calculate the impurity and the gain and build a tree. And this is the craziest part. So I had a question last time about how do we approach. So remember last time we had, for example, a binary classification problem, and we used Gini or entropy to sort of go from up to down, right? And here we sort of use a math on this, right? So we can calculate what would be the change in the loss function on the next step, and the next step, and the next. How do we change the final loss function? And we can even go through many trees like that. And you can see that here you sort of have, so a penalty for the square of the weights is embedded in here, right? So we add up. So here it was 1, and here no 2, sort of. And penalty for every added leaf is here. So these are our regularization terms used in gradient boosting. Now, yeah, and if we look back at the mean square error, then the optimum weight is just the average of residuals, right? Because this u is the first derivative, which is 2, right, of the residual, right? And this is just 2. Well, it's actually vice versa. So yeah. Okay, this is 2ht minus y, but then we take minus, and then it becomes y, so the residual, right? And this is just 2. So this is just the average of residuals with some regularization term, correct? Good. And this is just a mean square error, right? So if we calculate the optimum, put in the average, then this is just a mean square error, because this is just a first residual squared, which is the definition of mean square error. Okay. That's it. Sort of. Any questions? This was a math-filled lecture. This last slide is just a reminder that we still used alpha. In the same reason. We sort of know the direction we want to step, right? We know the gradient. Right? So this is, in this way, we kind of calculate the gradient of how to change, right? So if we go back, oh, actually not, let's not go back. So we move this tree according to the gradient of the final loss function. So we have some loss function of h, right? But we calculate the gradient, sort of the gradient of it in the point ht, right? We calculate the gradient, and then we move the tree like against the gradient, right, for loss function. So we moved it against the gradient when we add it up. So we calculate what is the best tree to move that function against the gradient. This is why it's called a gradient boosting algorithm. And yeah, and because we move against the gradient, we still need a learning rate because we can't overstep. Right, we can calculate the direction, but then take it to bigger a function. Now, this is state of the art, a de facto state of the art. So if you ever encounter, if you have large enough data, let's say 1,000 or 10,000 points, and you have a table data, use CatBoost. Right. If data becomes small, probably SVM, but we'll see. The last thing I want to talk about is the plan for our next lectures and next tasks. So next time, I'm going to talk about the Bayesian classifier and talk about optimization problems. Then after that, окей, у нас здесь Олег есть. Олег, мы хотим домашку на RL давать или на уменьшение размерности? Я не помню.
Я думаю, что на RL.
На RL. Then, December 14th, you'll have a lecture about reinforcement learning from Oleg. And then on December 21st, you'll have a lecture about dimensionality reduction from Yelena, who's also our a member of our lab. It's her specialty. So reinforcement learning is Oleg's specialty. He's very good at it. And dimensionality reduction is Yelena's specialty. She's very good. So they will be the best people to talk to you about reinforcement learning and dimensionality reduction.
А можно, простите, я перебью? У нас сессия 20 декабря начинается, если не ошибаюсь.
Yes, that's why you will not have a lecture. You will not have a homework after the last lecture. So after the last lecture is just so the course is full. So we will go through every theme that we wanted to go through. We lost one lecture that we had. So this is why the last one will not have any homework. All right, so we'll have the last lecture, 21st, no homework.
Еще раз, можно вопрос? Потому что лекция, которая предыдущая, которая там не 21-го будет, а 14-го, видимо, у нее домашка залезает на сессию.
Yes.
И лекция 21-го это уже на сессии.
Yes. But no homework after 21st. Okay. Any other questions? So exam, we talked about the exam, right? I need 2 days, 6 hours each. And you give me those 2 days, hopefully, at some point. Do you need a consultation before the exam? So we need 3 days. A date for exam, and a date for consultation. So please, I'm mostly free during the this last weeks of December. I have work, of course, so like be reasonable. Don't put anything too early or too late. Any other questions?
Вопрос по лекции. Вот я не до конца понял, а в чем у нас все-таки профит от того, что у нас несколько деревьев, не одно? Глобально.
The main reason is, okay, in what case? Right, so in a case of a boosting or in case of just a random forest? Or both?
Для обоих.
So for both, we can have a more complex function that way, right? So if we want to reach the same level of complexity with one tree, we'll have a very deep tree and we'll all go into overfitting. We can have we can control overfitting and use an ensemble of trees to have this better function, right? And random forest just sort of prevents overfit. You cannot overfit with the number of trees in random forest, right? So you can go as high as you want to go, and it will get better. Now with gradient boosting, the argument for complexity still stands, because now it's a much more complex function, solving function, and we have a new way to build it. So a boosting is a more complex way using the trees. I would not actually say that the arguments. So if you remember, we had an arguments for trees such as interpretability and stuff like that, right? So a tree, one tree is very interpretable. You can look at one tree and just, okay, this is okay. But if you go into gradient boosting, like this interpretation just goes away, right? So if, for example, a gradient boosting that Yandex uses, it's 100 megabytes, I think, just the tree, right? Go interpret. So you cannot even read it, you know, it's just rows and rows and rows of numbers, of thresholds and numbers and thresholds and numbers. So it's hard. So it's just a way to have a more complex function built on a tree logic. Okay. Any other questions? Good. Thank you, and see you in a week. And I give word to Oleg.
До свидания.
До
Goodbye.
свидания.
Да. Давайте скажем, что у нас перерыв 20 минут и начнем в 14:30.